Right, so what's really nice about lesson 6.6, 6.7, and 6.8 is that they're all really about finding techniques to help you graph and solve polynomial functions more easily. So in 6.7 and 6.8, our goal is really on focusing to find those factors and to be able to solve them. So in lesson 6.5, we got reminders of how to factor, we learned about sums of cubes, and we learned about rewriting in quadratic form. So we had learned in chapter 5, though, that not everything is always factorable. And that's when we introduced the quadratic formula. So with polynomials, not everything is going to be factorable either. So we started to go backwards and we looked at synthetic substitution. And we saw that synthetic substitution was kind of a cheat sheet method for allowing us to find the values of a number. So what we're going to do today is just reiterate all of those techniques and then add 2 more techniques to when we are trying to solve polynomials. So we have 2 rules we're going to learn today that are techniques to helping us solve. In the warm-up, it said you're given the quadratic function x squared plus 2x minus 15. The factors of that quadratic function would be x plus 5, x minus 3. So that's a factorable function. So when you hear the word factors, that's what you're thinking. You're thinking those 2 parentheses being multiplied together. If it's a cubic or a quartic, then those 2 parentheses change to 3 or 4. What we refer to as the roots or solutions are the x equals. So if I say roots or solutions, you're talking about the x equals. And then if you hear the word zeros, zeros and x-intercepts are ordered pairs or coordinate points. So I think one of the things that I want to focus on and have as a more clear understanding is what's the difference almost between roots and solutions versus zeros and x-intercepts. And it's all about how you present your answer. It's not that they're different, it's just how you present it. So we're in Algebra 2. Today we're going to learn the fundamental theorem of algebra. What the fundamental theorem of algebra says is that every polynomial equation with a degree higher than 0 has at least one root in the set of complex numbers. If you think about the word complex numbers, that's that a plus bi. It's a real plus an imaginary. So what this is saying is that it may not have a real solution, it may only have imaginary. And a corollary or like a subset to that fundamental theorem is that a polynomial equation of the form p of x equals 0 of degree n with any coefficients has exactly n roots in the set of complex numbers. So all that means is if your degree is 3, then you have 3 roots. Those roots can be a combination of real or imaginary. A follow-up to that corollary would be if a polynomial has n complex roots, will its graph have n x-intercepts? So if it has n complex roots, would it have n x-intercepts? So this is a cubic. By definition, a cubic will have 3 complex roots. In the case of that graph, all 3 complex roots are real. They have 3 x-intercepts, a -2, 0, and 2. So again, it's a degree 3. It has 3 real roots. In the next example, the answer to that question is no, because now you have a polynomial of degree 3 that only has 1 real root. The other 2 roots we would get would be imaginary. So if we were to factor that, we would pull the first real root from the graph. We'd see that it's -1. And then we would use that real root to find the 2 imaginary by using synthetic substitution to get it to a quadratic, to do quadratic formula. So there is a cheat for being able to determine the number of real and imaginary roots. That sheet is known as Descartes' rule of signs. So the rule of signs says that first all terms must be in descending degree. And then the number of times the signs change from one term to the next determines the number of positive real roots. And it determines the max number. It does not guarantee that number, it just determines that is the max number. If we plug in a negative x, the negative x determines the number of negative real roots at a max. So that's a lot of words. The best way to understand that is to apply it to a problem. So if we have a function that is of any degree, let's say in this case degree 6, degree 6 at most has 6 real roots. So what this Descartes' rule does is it determines the number of real roots that are positive. So what that means is if you were to graph this, it determines the number of roots that can live on this side of the coordinate plane because they're positive real roots. So what we do is we look at this problem and we determine the number of sign changes. So this is positive and this is positive. Therefore, no sign change. This is positive, this is negative, therefore 1 sign change. Negative, negative, no change. Negative, positive, a second change. Positive, negative, no, third change. Negative, positive, a 4th change. So what that means is that at most, this graph can have 4 positive real roots. So at most, this graph can have 4 positive real roots. Even functions must be in pairs because an even function ends in the same direction. So you have to have at least one of each, even if it is a repeated root. That root will still occur twice at that point and in factored form. So next, what we do is we take a negative x and we plug it in for every x value. We know that anything raised to an even power will be a positive answer. So f of negative x is 6 will auto stay positive because anything negative to an even power stays positive. So f of negative x becomes x to the 6 minus, because that negative and this positive became a negative, 3x to the 5th minus 4x to the 4th plus 6x cubed plus x squared plus 5. So what we do is look for sign changes. That is positive to start. And this is negative, therefore a sign change. Negative, negative, no change. Negative, positive, a second change. Positive, 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 positive means we have no additional changes. So what that means is that I have 2 sign changes. 2 sign changes means that at most this has 2 negative real roots. And again, the key idea is that it determines the max number of negatives. Remember that even-powered functions go in even pairs. So this could have 4 positive. It could also have 2 positive or no positive. This either has 2 negative or 0 negative because they have to go in pairs for even functions. Odd functions will have odd pairs, meaning they're going to have 3 or 1 or 5. So you could, and again, you don't have to fill out this chart for every problem, that would be insanity. But what this chart does is help you see why it could be the 4, the 2, or the 0. So if you had 4 positive real roots, we saw that at most we could have 2 negative. So that means that you could potentially have 4 positive, 2 negative, and no imaginary. Conversely, you have 4 positive, no negative, and 2 imaginary. Imaginaries must always be in pairs. Now, you could have 2 positive, 2 negative, and 2 imaginary. As long as they always add up to the degree, it's a valid possibility. 2 positive, no negative, 4 imaginary, no positive, 2 is our max negative, 4 imaginary, no positive, no negative, all 6 imaginary. And if you were talking about a 6th degree, that would just look like this, where it's just way up high. That's a 6th degree that has no real solutions because it never crosses down here. Okay? The last theorem is the rational root theorem. The rational root theorem is a technique for determining what numbers you want to plug into synthetic substitution. It's a technique to determine what those positive real numbers can be. So P are factors of a to the n, or the last term. Q are factors of a to the 0, or the first term. And I promise it'll make sense what P and Q are once we look at that. So, leading coefficient, constant. So what you do is, if you have this function, the last term is 15. That is your a to the n. The first term is x cubed. That is your a to the 0. So again, this is your a to the n. This is your a to the 0. This is going to be your, sorry, back to you. P, and this is going to give you your Q. So the possible rational roots are the factors of P, so numbers that multiply to give you 15, over numbers that multiply to give you 1. So leading coefficient is 1. So the numbers that multiply to 1 are 1. What that means is these are the only valid numbers you want to try to find your zeros from. They're the only valid numbers you would want to find your zeros from. Then you use Descartes' rule to determine what are the possible positives or negatives. So look at the sign changes. Positive to negative means we have one change, two changes, three changes. If I have three changes, how many possible positive roots can I have? 3. This is an odd function. So an odd function tells me that they have to be in odd pairs. So odds are going to be 3 or 1. Never a 0 then. Has to cross at one point because odds go opposite. One goes down, one goes up. So odds have to cross at least once. Odds have to cross at least once. Whether it's on the positive or negative, they have to cross at least once. If you plug in a negative x cubed, a negative in there, x cubed becomes negative, x squared stays negative, x to the 5th becomes negative, and 15 stays negative. Do I have any sign changes when I plug in the negative? No. So what does that tell me? That tells me that this graph never crosses in the negative region. It does not cross in the negative region. That's what that tells me. If I'm graphing this, it will never cross that negative x-axis. Knowing it has to sum to 3, if I have 3 positive, that means I have no negative, no imaginary. If I have 1 positive, then I have to have 2 imaginary. That's what it tells me about my solutions. Descartes' rule gives me a technique to determine the solutions. So again, if there can be no negative real zeros, then the plus or minus go away and they all become positive. So Descartes' rule can eliminate potential rationals because they can't be negative. You don't want to bother trying any numbers in synthetic substitution to find a real root that are negative because it can never be negative. Does that make sense? Guys? I know this is like a lot to comprehend. I promise once you do it more than just my example, it starts to click. Like, oh my gosh, I get it. So we're taking this function into account. Go back to what we know. This is a positive cubic. A positive cubic starts where? Down low and ends. That means that this graph has to cross at least once on the positive side, maybe 3 times, never over here, never. Pick a number, 1, 3, 5, or 15, to plug in synthetically to look for a 0. Because we're low on time, I'm going to tell you the number we're going to pick is 3. What that means is that x minus 3 is a factor because x equals 3 is a root. So go back to lesson 6 means x minus 3 is a factor. The remaining stuff is x squared plus 5. If I wanted you to solve that further, that means x equals 3 is my real positive root. And x squared equals negative 5, or x equals plus or minus I square roots of 5 are my 2 imaginary. Go back up, look at the skirts rule. What did they tell me? I told me I have 1 or 3 reals, 2 or none imaginaries. I ended up with 1 positive real, 2 imaginaries. There is one last example that you need for one of your pages. I will make you a short, like 3-minute video and post it on Teams at the end of the day. You can either watch it in the class tomorrow, or you can watch it tonight, so you don't have to listen in class if you don't want to. So that would be your homework for me, is to finish the last example via video.